Hello, everyone. In this video, I'm going to talk about another example using dynamic programming. And this example is rod cutting. Suppose that ABC hardware store buys steel rods and cuts them into shorter rods to sell, assuming that the curve is very small that can be ignored. But we still want to minimize cuts to save labor costs, to save labor costs, even though the curve is small. The management wants to know the best way to cut up the rods. We assume that we know for I from 1 to n feet, the profit PI is the profit PI in dollars that the store charges for the rod of a length I feet. Rod lengths are always an integral number of feet. To figure out how to cut a rod of length n feet to sell for the maximum profit, we will first formulate the problem as recurrence relation. A cut on a rod divides it into two shorter rods. Let's say we first buy so we have a rod. Let's say this is n feet long, and we can cut it into two shorter rods. And then let's say this is at the i's feet. And for this part, the store charges PI dollars, and for this part, the store charges n minus I dollars, and for the entire rod, the store charges PN dollars. Okay, so depending on the value of PI, sometimes dividing into shorter rods will actually provide more profit. So we just want to figure out how to cut up a rod in order to get the maximum profit. Okay. Now we also want to maximize the profit while minimizing the number of cuts. Okay, as we said that we want to save labor costs. Cutting, assuming you need to have someone to cut it up. All right. So now in order to formulate this problem as a recurrence relation, so the first thing we want to do is to create a name and then specify the parameter. So that is a naming process. So now we let R of I denote the maximum profit we can make from a rod of a length I with the smallest number of cuts possible. Then we have that. So now we change. So now we use I to indicate the length of the current rod, and then the cutting point will be J. So what we are looking at here is for this, we have profit PJ, and then for the remaining rod, the length of it is I minus J, but then we can still cut it up. We may still cut it up. So then what we are getting now is that R of I is the maximum of all possible J, right? So this J will start from 1 to I. So when j is equal to I, that means there is no cutting. So we're going to look for all possible j. So all possible j. And then once we have a j, then the profit is p of j plus, now for the remaining I minus j, for the remaining rods of length I minus j, we may further cut it up. So this is out of I minus j. So for each j, possible j, this is the profit that we can make. So among all of those, we want to find the maximum. So j is from 1 to I. Okay, so when there is nothing to cut, then the profit is 0. So this is the boundary conditions. So that is the recurrence relation. So now let's implement this strategy. So we call it cut rod and using Python. And so this is a boundary condition. So the input here is a list of profits for each length of a rod, and then the total length is n. So if n is 0, we return 0 because there's nothing left, and the profit is obviously 0. Otherwise, we are going to do the maximum for all possible cuts I. And since we are going to consider the length of n, so this I is from 1 to n plus 1, and we want to make sure the index starts from 1. So we add a 0 to it. So that means that this Q is an Q is a list. All right, and this is 0, 1, up to n, and so Q is actually R here. Okay, so we can use R. For instance, we can change this to R. All right, and so it's a cut rod. And return R. Okay, so let me just keep it as it is. All right. And then we're going to run it. So this is a direct recursive call. So this is a direct recursion. So we didn't use dynamic programming technique yet for this one. So this is directly from this recurrence relation. Okay, so now let's run this to see how much time it takes. All right, so here I set n to be 27, and this is the example from the textbook. And for this, since n is a little bit too small, so we will not be able to feel the pain of this direct recursion, how long it takes. So instead, I'm going to set n to be 27. And we're going to randomly generate some profits for each length of rods. And so this I is from 2 to the n. Okay, and so as you can see here, that this is P, the profit that we have. So this is okay. So this is means that for 1 feet it sells $13. For 2 feet sells 17. 3 feet sells 29. And 4 feet sells 44, 5 feet 47, and then 6 feet, well, and it's cheaper. And because we randomly generate these numbers, okay, so they may not be that realistic, but nevertheless, we can still figure out what would be the maximum profit. So the maximum profit is, in this case, is $325. But let's see how much time it takes. So it takes 13.5 seconds. Okay, so I'm not gonna run it. So I'm not gonna just let the people watch this, and that takes 13 seconds. All right. So next, we're going to see direct recursion. What would be the time complexity? Okay, so in order to do so, we follow the same procedure. So let T of n denote the total number of calls made to cut rod when call with a second parameter equal to n. So hence we have that T of n is equal to, so you could see this is n, so this is the length of a rod. Okay, so then we could have a cut of T of 1. So that's so we need to look at T of 1, we need to look at T of 2, we need to look at T of 3 until n minus 1. We need to look at all of these. Okay, so that means that we're gonna sum them up. So sum them up. And also including, so we don't cut, so that means we look at T of 0. Well, T of 0 is just 1, right? So because we don't cut it. Okay. And then, so this is the time to call, to implement all these recursive calls. And then, so this one, we just add all these profits back. So that's a constant, but we use 1 to represent it for simplicity. Now we're going to show that T over n is actually equal to 2 to the n by mathematical induction here. Okay, to show this. And so we start from induction basis. So when n is equal to 0, there is no cut. And so T over 0 is just 1. This is, let's say this is a boundary. Well, you can either 1 or 0, it doesn't matter, right? So now this boundary sets it to 1. So then let's look at induction hypothesis. So which means that for any k less than or equal to 0, greater than or equal to 0, and less than or equal to n, we assume that T of k is equal to 2 to the k, And then in the induction step is we're going to show that T of n plus 1 is equal to 2 to the 2 to the n plus 1. Okay, so because n is greater than 0, so we know that this is T of n plus 1 is equal to summation of T of I from 0 to n plus, and then there's a plus 1 here. So which means that by induction hypothesis, so this is equal to, because T of I is simply 2 to the I, so this is I from 0 to the I, and so you add all of these, 2 to the I from 0 to n, we know that it is equal to 2 to the n plus 1 minus 1. Okay, and then there's a plus 1 here, so what we get is exactly 2 to the n plus 1. So this indicates that, so this completes the proof. Okay, so this takes exponential time. So now we are going to improve. We are going to improve the implementation of it using dynamic programming. So meaning that if we take the top-down approach using recursions, and then we're going to use an extra space to store the results to subproblems, and that extra space is listed here. It's just called memo. So now we're going to define memoirs cut rod. So what we're gonna get here is a P, which is the profit, and is the input length of a rod, and then memo is the list that is a list used to store results to subproblems, so that when we need to when we encounter the same problem again, we don't need to recompute it. Instead, we'll just do a table lookup. So that is just a constant time. Instead of, for instance, if we need to look at T of I, if it's already been computed, and then it's just a constant lookup. So it's just one step rather than T of I steps. So that saves time. Okay. So then this is a standard. So first of all, we check if memo of n is greater than 0, so which means that it has to be computed. We simply return what it is. Otherwise, it had, so we start from 0. So, well, actually it is according to, we could, for instance, we could just change it to 0 here, okay? So let's do it once, because we want to do basis 2 to the 0 still 1. So let's just do it as 1. And what we would change is change it to 1. It really doesn't matter, because when n is equal to 0, it's 1. Okay, so then what we actually do is that if we had, so we will store the result to any new subproblem into the into memo. Okay, the rest of it is the same. All right. Okay, so now let's see. We use the same input. Okay, so let's run this, and then I have already, I want to use the same P, so let me not generate it again. Okay, and that's the same. P. Did I? Okay, I didn't run it, right? So let's run it. So this will be the same P. Okay, yeah, so I want this to be the same P, so let me, because I don't want to, so this will take 13 seconds to wait, so let me separate this, okay, so let me separate this. So don't have to run this again. Okay, so this is the P here. And, oh, I guess so I will just need to run it now. Okay, it takes 13 seconds. So let's run it. Okay, it's been queued. So now let's wait for about 13 seconds, and then we're gonna come back here and use the same P. Okay. All right, so 13 seconds. So this is 350 for this. So now we are going to, so that is the same P, and let's see how long it will take to run this. Okay, so it takes 13 seconds, so we don't have to do this again. So this is the old ones. Now what we want to see here is this. Okay, so this is 350 that we got, but we got the result right away. So as you can see, it's only 21 microseconds. I'm sorry, milliseconds, 21 milliseconds. So 13, so milli, yeah, those are tens of thousands faster. So that's why in the blink, you should be able to see it, right? So 32 milliseconds, I'm sorry. So so that is the, so we print, so this is the maximum profit, and then out of one, out of two, and so on. And so this is out of 27 feet, right? So this is 27. Okay, so this is a top-down approach using memoization. Again, so dynamic programming is actually pretty straightforward. You just create an extra space to store results to subproblems, so that next time if your recursion needs to recompute a subproblem you have seen, what you need to do is just go to the storage to do a table lookup and get the result, rather than redo the computation, which may incur other recursion, so that adds up your time. All right, so that's dynamic programming. So now we can also get rid of recursion. So in this case, what we need to work out is that now we're going to work out from the bottom up without um, using any recursion. So the idea then is this. So let's say we start. So we have R. So we want it to be 0 to n. So initially, out of 0 is 0. Out of 1 is just P1. Okay, and then for out of 2, we're going to look for two options. One is P1 plus P1. The other one is P2, and to see which one is larger. And then we're going to place whatever the larger one, the max of these two, to go in there. Likewise, for I is equal to 3, we're going to put max of P1 3P1, right? Because this is 3. Or P1 plus P2 or P3, the maximum of this in going there. So in general, if you do 4, so what we need to do is that we're going to look for which one is better. So which means that we may either have all 3 of those, and then or 2 copies of this, or 1 and 3, or 4 itself, and then we put them in there. Right? So we write this into code. So this R will be this is initially set to 0, and then for each J, okay, so we want to compute R of J. All right, and then we're going to see which one is the best. So we're going to look for all possible I, right? So this is I from 1 to J plus 1, and then this is either Pi plus all of this, and then this all of that will, so this will have to be already computed. Okay, so we just look at whichever is the max. So in other words, so let's do it again. So 0, 1, and so that's what J starts from. So as we know that R of, so this is R. So this is always a P1. So this goes to max P2 P1 or P2, and then for 3, you have one is 3 of this, but essentially what we do is that P1, and the rest of it is a P2. We see whichever, so this is R2, right? Whichever is better, so because now we have a value here already, or P3. So we got max of these two. Okay, so likewise for 4, we got P3. So that, so we got P1 plus R, okay, 3, 2, right? So 4 is P1, and then the remaining of it is 3, because all P2, the remaining of it is 2, and P3, the remaining of it is R1 or P4. So all of this, then we are going to consider which one is the largest, and we go in there. So the max of these 4 will go in there. Okay, so there is no recursion, and we run it. So as you can see, because there is no recursion, it's actually faster. Earlier, it takes 32 milliseconds, but now it takes 8 milliseconds, but they are still in the same order, right? So this is still in the range of milliseconds, rather than the direct recursion is seconds, and also it's 13 some seconds. Okay. So the next thing is that now we want to know how to cut. So which means that when during the computation, we figure out which one provides us with the largest profit value, we'll remember that cut. So then that's what it is, right? So we create a new list to remember the cutting points, the cutting where you cut. So again, we want to compute all of J. And this time, because we want to remember the maximum cut, so we will set Q to -1 to begin with. And then for I, so now we look at all possible cuts. So let's say we cut it at the I's feet. So we remember the temporary value, temp of P is assigned P of I plus R of J minus I. And when Q is less than or equal to temp, then we'll assign Q. Now, this is because we also want the maximum number of cuts possible. And so we will include equal sign here so that so you keep going just in case that, for instance, sometimes you have a cut here that gives you the, say, gets the same value of profit Q. And then if you don't cut, it also gives you a value of Q. And then this time you are going to choose that you don't cut because I have this equal sign. If you don't have an equal sign, you still get the same maximum profit, but then you may end up more cuts. Okay, so that's the little small trick. So now we remember the cuts. When I finish this loop, then I know which one gives which cut, which value of I gives us the maximum profit for the value of J. Well, that is we call it extended bottom-up cut rod because now I keep track of cutting points. Okay, so we run this. So now let's look at a simple example. So we set it this. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 feet long rod, and then we can cut it into one rod, and the remaining is 9. We can keep cutting that, right? So then it's 2. So this is so this means that for the rod of 1 feet long, it sells $1. 2 feet long sells 5. 3 feet long sells 8. 1 foot long sells $1. 2 feet long sells 5. 3 feet long sells 8. 4 feet long sells 10. 5 feet long sells 13. 6 feet long sells 17. 7 feet long sells 18. 8 feet long sells for $22. 9 feet long sells for $25. And the original one, 10 feet long, doesn't. So it means we don't cut it, and we can sell it for $27. All right, so in this case, we're gonna run it. Okay, so then we can see the maximum profit we can get is 27. And then the cutting point is like this. So first of all, we are, in order to get 27, how we're going to cut it. So we're going to cut it into, the first cut is 6 feet. Is a 6. The other one is 4. So for 4, the profit is 10 right here, 10. For 16 is this. So this is $10. So this is a 4. So this is a 4. So this is a 6. This is 4 feet. 6 feet. So this is $17. Altogether is $27. So this is the maximum you can get. So likewise, when I change the value, you got 442. So which means that one is 4, 4, and then the last one is 2. So let me change this. So it's shorter. So this is 2. So for 4, we got 12, 12, and then 2 is 5. So this is a $29. So this is dollars, dollars, dollars. So this is feet, feet, feet. Okay, so that's how we obtain the cuts. So then the complexity analysis, how do we do the complexity analysis? So first of all, we're going to do the recursion. And the recursion is here. So for each subproblem out of I depends on I many subproblems. Okay, and then assuming for each of these I subproblems, you just need to do a table lookup. So then you would just need to be I. So this essentially just I's from 1 to n. So what that means is you are going to, so you're going to, so I from 0, yeah, 0, sorry, to, so I equals 0 just means you don't cut, so that's n, right? So, or you can say I is from 1 to n, and then you add them up. So you add them up. So that is n times n plus 1 over 2, and this is theta of n squared. Okay, so it's upper bound n lower bound n squared. Instead of 2 to the n plus 1 using direct recursion. Right, so that's essentially when you do this, when you try to analyze using dynamic programming, you just need to look at how many subproblems the current problem will depend on. And because these subproblems, they are only computed once. So you can think of them, each of those, you do a table lookup, and that's the constant time for each subproblem because they were already computed. All right, so that is the end of this video. Thank you for watching.